So let's start by reviewing some topics from probability, namely independence. So recall that two events are independent which there's a couple equivalent ways of saying this. The more usual way is to say that the probability of E intersect F, so E and F are our two events, our subsets of our sample space. So two events are independent if probability of E intersect F is equal to the product probability of E times probability of F. But another equivalent way to say this, that the probability of E given F is equal to the probability of E. So knowing F does not change the probability of observing E. So let's do a couple of examples. Roll 2 dice. And then consider the events first of all, that the first die is a 2, and our second event, that the dice add to 10. And the question is, are these independent? And intuitively, the idea of independence is that these events don't affect each other. That's most clear from this definition here, that knowing the outcome of one event doesn't change the outcome, or knowing the outcome of one event doesn't change the probability of the other one. So just from that intuitive standpoint, we kind of expect these are not independent, because if you know the value of the first die, you expect that that gives you some idea what the sum will be. Well, let's check. Let's go ahead and check the definition. And I think for this one, it might be easier to check this definition. So let's call this E and this F. So the probability of E is the probability that the sum of the dice is equal to 10. So out of 36 possible outcomes for 2 dice, how many ways are there to get 10? We can get, let's see, 4 plus 6, or 5 plus 5, or 6 plus 4. So we should get 3 over 36, or 1/12. This is the probability that the dice add to 10. Because it's these 3 out of 36 outcomes. Now, what is the probability of E given F? So this is saying if we know the first die roll is a 2, what is the probability that the 2 dice add to 10? And this, we can rewrite this as probability that the second die, so the second die just needs to be whatever it needs to be in order to add 10, which is an 8 if the first die was a 2. But of course, there's no 8. I guess we're assuming that these are 6-sided dice. There's no 8 on a die. So the probability of this is 0. If the first die is a 2, they cannot possibly add to 10. So we see that the probability of E given F is different from the probability of E. So these are not independent. Well, let's do another example, just to illustrate that there are occasions when your intuition can be misleading. So how about these two events? So the first die roll, so in the same situation of rolling two dice, the first die roll is a 2, and the dice add to 7. Are these independent? So maybe it's clear from the way I'm asking this question. Intuitively, my intuition is that knowing the first die should affect the probability of the sum, but let's check if this is independent, because by now you may be suspecting that it will turn out that they are independent, counterintuitively. So let's use the same definition and the same method that we just used before. So I guess we should similarly call this E and this F. So the probability of E, what is the probability that they add to 7? Well, again, there's 36 outcomes, and how many of them add to 7? That is 1 plus 6, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, and 6 plus 1. So that's 6 outcomes out of 36. So that's 6 over 36, or 1/6. And what is the probability of E given F? So this is the probability that we know the first die is a 2. What is the probability that they add to 7? Just like before, that means the second die needs to be whatever it needs to be. In this case, it needs to be a 5 in order to add to 7. And now, this is a perfectly good outcome for a 6-sided die. So the probability of getting it is 1 in 6. And so, we can see in this case, it turns out that these events are independent. Since these probabilities are equal, these are independent. So it's good to have an intuition about what independence means, but this is just to illustrate that it is also good to check, because sometimes your intuition can be mistaken. And just a few more points about independence. Recall when you're dealing with more than 2 random variables or more than 2 events, there's a distinction between different types of independence. Namely pairwise and mutual independence. So pairwise independence means that for any pair, like it says in the name, for any pair of events, so let's say we have events E1 through En. Pairwise independence means that for any 2 of them, the probability of the intersection is the product of those probabilities, whereas mutual independence means the intersection of any collection of them. So of course, mutual dependence is stronger than pairwise independence because you're able to take an arbitrary intersection rather than just an intersection of two things. So, for example, here's a question. If A, B, and C are independent events, are A intersect B and C independent? So immediately you should notice that I did not specify, now that we're dealing with more than two events, we need to specify if they're pairwise or mutually independent. Well, let's examine both of these independently. So pairwise independence in this case, it's false. So no. And for example, basically any example where they are pairwise independent but not mutually independent should work. So for example, in our familiar roll two dice scenario, let's say A is, first is a 2, B, the event second is a 2, and C, the event that the dice add to 7. So by the argument we made above, these two are independent, and by the same argument, these two are independent. And these two are independent as well, because each die does not affect the other die. So these are pairwise independent, but they are not mutually independent. And we can see that these events are not independent because A intersect B is basically a single outcome. The first is a 2 and the second is a 2. And C, is that they add a 7. These are not independent because this has some positive probability, I guess it's 1 in 36, and this has some positive probability, which we saw as 1 in 6. But together, the probability is 0 because you cannot have both dice be a 2 and have them add to 7. On the other hand, if they are mutually independent, then the answer is yes. And how can we prove this? Well, the thing that mutual independence gives us is that we can take a triple intersection and split it into a product. So we can start from that. We can split this into probability of A times probability of B times probability of C. And again, since these two are independent, we can join these back into probability of A intersects B. And this equality is exactly saying that the probability of A intersects B intersects C is probability of A intersects B times probability of C, which is exactly saying that these two events are independent.